Chapter 9 Uniform Circular Motion 9.1 Introduction to Circular Motion. So far, you know how to handle linear motion and projectile motion. Circular motion is one that includes cars turning around corner and whirring of a mass at the end of a string, etc. 1. Describing circular motion. You have just learned projectile motion. Although projectile motion is a two-dimensional motion, it is just a combination of horizontal uniform motion and a vertical accelerated motion. You may apply the equations of uniformly accelerated motion listed on page 61 to handle questions of projectile motion. Circular motion is a bit different. It is not a simple combination of linear motions. In Chapter 9, we will focus on uniform circular motion, which is a circular motion with constant speed. A. Angular displacement and angular velocity. We use angular displacement and angular velocity to describe circular motion. Displacement in linear motion refers to position. Angular displacement here also refers to position of an object in motion measured by an angle. Displacement in linear motion also refers to change in displacement sometimes. For example, velocity equals displacement over time. Similarly, angular displacement sometimes also refers to change in angular displacement. So we may write angular velocity equals change in angular displacement over time taken, t. The unit of angular displacement is radians. In particular, 2 pi radians refers to 360 degrees, which means a complete revolution. Angular velocity is the rate of change of angular displacement. It equals change in angular displacement over time taken. Its unit is radian per second. B. Linear speed and angular speed. Imagine I drive at 10 meters per second along a circular track to turn around a corner. The radius of the track is 100 meters. What is the angular displacement that I will make in 2 seconds? In 2 seconds, I will travel 20 meters along the track. I should have made an angular displacement of 10 multiplied with 2 divided by 2 pi r, which is the radius, multiplied with 2 pi. So what is my angular velocity? It is 10 over 100, which is speed over radius. So angular velocity equals v over r, where v is the linear speed of the motion. On the other hand, when a mass performs uniform circular motion with constant angular velocity, the speed of the mass v is r omega. The direction of this velocity when a mass performs circular motion should be tangent to the circular path at all times, being perpendicular to the radius of the circular path. C. Period. Period is the time taken for the mass to complete one revolution. Obviously, apply t equals distance over velocity, which gives velocity equals distance traveled over time taken, which is 2 pi r over period. Similarly, from angular velocity equals change in angular displacement over time taken, we see that the angular velocity equals 2 pi over period. Example 1. is a straightforward application of the above formulae. And now please try checkpoint 1 below.